Um, yeah, so I was asked to give this lecture about what is a fermion. And I think that this question can be answered on multiple levels. And if you want to answer it at a very technical, abstract level, there is probably only one right answer, which is that you have fermions when you have a system which has a representation of a certain Clifford algebra. But you might think that this is also maybe a very abstract and technical statement, and what you really want to know is in what kind of systems does this abstract structure appear. And if you ask the question at this more practical level, I think people coming from different backgrounds and probably even all of you will give different answers and have different examples of where they think fermions appear. So I think my plan was to first discuss this technical definition or abstract definition, just so we are all on the same level, and then give what I think maybe are a couple of relevant examples of where this structure appears, and anyway, the ones that I like. So yeah, so I will start by talking of fermions, by saying that fermions are a representation of the two ends of even dimensional Clifford algebra. And hopefully this will be clear in a moment what this means, what this is, and what the statement means. But just to be clear, this Clifford algebra is not the Clifford group, which is probably what people are more often working on in this group. For what we care today, this is a completely unrelated concept, so don't be confused. So what do I mean by this? And so to make this more precise, I would say that we have a system of n fermionic modes. If we have the following. Now here, this number of fermionic modes, for now, just take it as this is an integer, positive integer that kind of defines the size of the system, the fermionic system that you're considering. Maybe later it will be clearer what exactly it refers to, but for now, that's just a number. And we have a system of n fermionic modes. If we have, well, a Hilbert space, H, and we have two n Hermitian operators, which I will call gamma A. And these are linear operators on this Hilbert space. So these are space of linear operators on H for all A. And there's two n of them. And these operators generate a representation of the Clifford algebra, which means that they satisfy specific algebraic relations. And in particular, they satisfy the following. I will try to put hats on the operators, but I will forget very soon. So the anti-commutator of gamma A, gamma B is proportional to that.
Tommaso, sorry.
Yes.
Just let you know, we're at the lower bound of what's still readable online. I already got a chat message that it's quite hard to read though.
Regarding the size of what I'm
The
writing.
size, yeah.
Okay.
If you could write it a bit bigger, that
Sure.
would be great.
Thanks. Okay. So this relation in particular, just to be clear, if we consider A equal to B, this means that gamma A is partially identity. And if we consider it A different from B, this means that they anti-commute. So gamma A for A different from B. Right. And I said the Hermitian. Finally, I say that they generate this algebra in the sense that if I now consider the object that I get by taking all possible products and linear combinations of these products, I get this algebra. This is the span of all objects which are products of this kind. Okay. Complex span? Yes, complex span. And of course, here I wrote this as any product, but given those relations, there will be actually a finite number of products. Once a certain gamma appears twice, you can kind of use those relations to commute them until they meet, and then they square to the identity. So there's only a finite number of such products. Yes?
How important is it that it's an even number?
Right now, for the definition of the Clifford algebra, it's not, but later, like we assume that it's an even number.
And the definition as for modes, I'm supposed to think of the modes as qubit equivalent, or?
Yeah, in a sense, yes. Ultimately, they will be somehow also there's a relation to qubits, but yes, here it's a number that defines somehow the size of this fermionic system in a way. So it's in the same way as the number of qubits could define the size of your system.
Do you require anything on the action of these gammas on H? So as matrices on H? Do they have to have a certain structure? Like
there should be Hermitian.
Okay.
That's
but it could be that they act trivially on like a big chunk of H.
Yeah.
Okay.
But we will see that this is actually not the case. Yes.
Is that the same as like, is this algebra also like Lie algebra or not?
No, this is an algebra in the sense that I can take all linear combinations of these objects are still inside the algebra, of course, by definition, and any product of these objects, where by product I mean really the composition of them as operators, is again, of course, a product of these products is again a product. So it's again in the algebra. Usually when you talk about the Lie algebra, you mean that it's closed under commutators, right? Not with respect to products. So of course, if it's closed with respect to products, it's also closed with respect to commutators, but not the other way.
So would this then more be like a star algebra?
I would say it's a normal, like algebra is as in linear space with a product.
Right, yeah.
And here the product is the product of these operators as operators. So it's an algebra. Yeah, and in principle, I mean, this is an abstract object that I've just defined here. It's an abstract algebra that I've just defined here. What I mean by the fact that this is a representation of this algebra means that these are not abstract objects, but these are actually Hilbert space operators. So I have a representation of this algebra as operators on the Hilbert space. And right, to connect to the question, somebody's question, actually this is all that I require, what is written here. But it turns out that this actually constrains very strongly what the structure of the system that can arise. And indeed, there is a theorem which I guess if you want to be a bit pompous, you could say it's a fermionic stone von Neumann theorem. And this says that all irreducible Fermion representations so all objects of this kind are unitarily equivalent. So basically, up to choosing the right basis, everything is the same. And okay, I don't think I can claim to now prove this theorem rigorously, but I think it's quite easy to gain an intuition of what this means and what this is the case. And with a construction that is essentially equivalent to these ladder operators that you build for the harmonic oscillator. So I think it's instructive to go through this. So I will do this now, and hopefully it will be clearer what this means. So here we use the fact that there's an even number of these gammas. And if there is an even number, I can always pair them up, the first with the second with the third, first with the second, the third with the fourth, and so on. I group them into pairs. And for each pair, I can define an operator I call n, nk, which is I define it this way. For every k. So out of two n operators, I create n pairs. So these are the two elements of each pair. I multiply them together, add some factors I and 1/2, and I get this operator n. Okay, and there's capital N of them. And in a similar way, I can also construct the following operators. Again, for each pair, I build an operator A. And also an operator A dagger, which is literally the Fermion conjugate. So it just has a minus because the gammas are Fermion. Right, so I can construct these operators, and you see that the A's, so the n is some quadratic expression in terms of the gammas, but the A's are just a linear recombinations of these gammas. So in particular, I can also write the gammas in terms of the A's. So this is just, in a sense, it's a linear change of basis in the space of operators gamma, but that's not so important. What is important now is that you can observe that these operators satisfy certain properties, which are, for example, that these n's, they are Fermion. They all commute with each other. This you can see because they contain, each n contains different gammas, like there are no two different n's that contain the same gammas. So each one of them contains two different gammas, and so each gamma commutes with the, anti-commutes with the other gammas, so two of them commute. So you can convince yourself that all the n's commute with each other. And another property is that n k squares to n. And this I can also compute this for you, but I will not do more computations. You take n and you just square it. You will get that the ones, 1 times a quarter, then there will be terms proportional to I, which are the same, and there's 2 of them. And then finally you have the term where you have this product of 4 gamma. And here you see that you can use these algebra properties of the gammas to exchange these two, and they anti-commute, so you will get a sign. So this becomes a plus, and then you have 2k times 2k, gamma 2k times gamma 2k, which is the identity, and gamma 2k plus 1 times gamma 2k plus 1, which is the identity. So this all terms is equal to 1/4. So you add it here, you get 1/2, and then you're left with something that is equal to the nk that you started from. And finally, you can check that also this relation is satisfied. Doing some more calculations like this, finding things out, multiplying, and using the algebra. So I'm not going to show more. So okay. Yeah.
Before we move on, there was a question in chat.
Yes.
He is asking, is this theorem only true once one fixes the dimension of the array? Or is there only one array?
Once you fix n, there is basically only one array.
There's only one, okay.
Yeah. And this is what I wanted to show now. Now, if you see that these n's are Hermitian operators that all commute with each other, so there must exist a basis of your Hilbert space that is of shared eigenvalues of these things. And I will label these bases by the eigenvalues of these operators that commute. Plus, potentially there could be other quantum numbers that I will call alpha. And okay, then the question is, what are the possible eigenvalues of n? But the fact that n squares to itself, this means that the spectrum can only be 0. Because these are the only numbers that square to themselves. You can also see that each n has to have both eigenvalues, because otherwise it would be just equal to 0 or to the identity. So this commutator would be 0, because 0 or the identity always commutes with anything. And then this means that there will be some a's that are 0. But the a's cannot be 0, because then this would imply that also gamma is 0. But gamma needs to square to 1, so it cannot be 0. So each n has to have both eigenvalues. So here, there will be states that, for example, are some kind of lists of zeros and ones. Now the question is, what such states appear in our basis? Like, what bit strings appear in the basis, in such a basis of the Hilbert space? And to understand this better, you can see that this relation implies that you can use the A operators to create eigenstates one out of the other. So if you have A, J, or AK acting on one such state, you can see that this will be again an eigenstate of the n's. Right? If you apply n j here, if j is different from k, then it just commutes, and you will get out the same eigenvalue. If it's different, then you use this relation and you will get a -1, right? Okay. That this is equal to and this is an eigenstate, so this just becomes a number. So this state here is again an eigenstate of all the n's, except that the kth n has been reduced by 1. And all the other terms. So, of course, given that the spectrum is that, if this was 0, you cannot reduce it further. So this will the only possibility is that this I mean, it has to be proportional, so there's some kind of constant. If nk was 0, this constant has to be 0. If it was 1, it would be something finite. So the what I'm trying to say is that if you do the same thing now with the A dagger, you will also find that you can increase the eigenvalue by 1. So essentially, if one of such states exists, by acting on it with all the A's and A daggers, you can create states described by all the other possible bit strings. Is that clear? So, yeah, exactly. In the Hilbert space H, you must have all the states with all the possible different bit strings here. So this ultimately means that just because these gammas exist, this representation exists, then your H must look like the span for all possible bit strings. And for some possible other index alpha. But for each alpha, there exists, you can create all possible bit strings here. So this means that the Hilbert space is just a direct sum over this alpha of states parameterized by bit strings. So of C to the 2n's. So you see that this is the irreducible representation of which is 2 to the n dimensional, and the most that can happen is that the Hilbert space breaks into many copies of this, and each of these copies has the same dimension, and inside each of the copy, the operators gamma act in a perfectly defined way that is determined by all these relations here. So this hopefully makes it clear what this means.
What was the end again?
So this is just a set of. So you have to assume that there can be other. Essentially, you have to interpret this alpha as possible other degrees of freedom of your system which are not fermions. So you could have a bunch of fermions and a spin, and this could be if the possible states that you have is the spin is 0, and then all possible states of the fermions, and the spin is 1, and all possible states of the fermions. More generically, you can have an arbitrary other index here, and A is just a set of values that this index has. Yeah.
Then here you have a state A.
Yes.
So that set A depends on how big is the H and how big you pick to land.
Yeah. So I mean, maybe the one way to see it is that you cannot have this representation on an arbitrary Hilbert space. The Hilbert space needs to be a multiple of 2 to the n. The dimension should be a multiple of 2 to the n. Yes.
It's, I think, related question in that can H be also be infinite dimensional, as in this set A from which alpha is drawn. It's like, can this be isomorphic to, say, the real line? Like something quite exotic, but
Yeah, I guess.
because you require unitarity of the representation, like that.
I wouldn't expect that this is the case. I think you can have arbitrarily complicated stuff going on there. Of course, it could also be infinite dimension because you want to consider infinitely many fermionic modes, but that's, I guess, a different situation. But yeah, I don't think so. Like maybe you have fermions and a boson. Then I think this exists in nature and should exist. So it should be possible.
Sorry, I didn't understand where this alpha comes in mathematically.
Oh, just when you say that you have commuting operators, then there exists an eigenbasis, and each of these eigenbases has to be an eigenvector of those operators. But it doesn't have to be that knowing the eigenvalue with respect to all the n's fully determines the state. You can have many states that have the same eigenvalue with respect to the n's, and then you have to introduce some other index to label them.
But if I fix alpha, then those operators map between states of a fixed alpha.
Yes. Yeah, this is not something that I showed. This you need to convince yourself of that once you have alpha, if you have multiple alphas, then for each alpha you can construct all the possible fermionic states, and if the two original states with different alpha were orthogonal, then also all these tower of states that you construct on top of them will continue to be orthogonal.
And why is it if I restrict myself to a fixed alpha, why is this not like a, I don't know, like some reducible like sub-representation? Or is this like,
I mean, if you fix alpha, you get one irreducible representation, which is this two to the n dimensional representation, labeled by all these n's. So for each alpha, you have an irreducible representation.
okay, okay, that's what I'm not sure.
Why is alpha labeling now? I don't get that. Why is alpha? Is it like a label for my error or?
Yes. Yeah, but because you can have, if you have one irreducible representation, you can also have multiple copies of the same. Because you can, like, you can consider a state which is a space which is the sum of many, right? You can have like this, like, I don't know, one of the matrices representing your fermionic operators can be like decomposed into blocks, right? And each of these blocks is 2 to the n dimensional, and it's the same. Like this block is the same as this and the same as that. So you just have many copies of the same representation. There's only one representation, so they have to be all the same.
My Hilbert space is, I lost. My Hilbert space is 2 to the n.
Sorry?
My Hilbert space, so my state space, or like,
Yeah.
has 2 to the n parameters.
Your Hilbert space has 2 to the n states,
States, yeah.
or
States.
it can have 2 times 2 to the n states. Like you have 2 copies of these 2 to the n states.
And why can I have more? Okay. Shouldn't this map my Hilbert space to? That's like L of H is something that maps my Hilbert space to my Hilbert space. Why can it have? Why? No, I'm this dimensional.
Yeah, so your whole Hilbert space
Yeah.
is as big as you want it to be.
Okay.
But with the constraint, right? And this, all the states here are meant to be a basis of your whole big Hilbert space, right? But with the constraint that this total dimension has to be a multiple of 2 to the n. So you have, for example, in this picture at the door, you have 3 times. This is 2 to the n. This is 2 to the n, and this is 2 to the n. And how do I label the states inside this 3 times 2 to the n dimensional space? I have n zeros or ones, right? And then I have an alpha that can be equal to 0, 1. This labels in which of the 3 copies I am in, right? And that's it. Like this label, 2 times 2 times 2 times 2 times 3, and you will get 3 times 2 to the n.
Okay.
So these are all the states in all my huge Hilbert space.
So this doesn't live in LH, this lives in with my operator.
What is
Like the three blocks thingy. It doesn't live in LH.
for me, this
H
is the whole. This is H. The whole thing is H. So it does live in LH,
Okay.
right? And this subspace, of which I have 3 of them.
Yeah.
I guess I would call it. I call it this.
Okay.
It's just C to the 2 and to the n.
Mhm.
And the total H is composed of the sum of 3 times this. And the point is that each of these 3 copies is the same. Like all the operators have to act in the same way, and each of them has the same dimension, and all their states are labeled by bit strings. Like each of the copies is identical because there is only one possible error.
Okay. Thank you. That helps.
Another question on this.
Yes.
So, that system of n, like n Fermion or 2m Marijuanas,
Modes.
not system of 2m.
Mhm.
Now bring them together.
Yeah.
As in, I have one representation, I have the other.
Yes.
Just take the delivered spaces, I take their direct sum, and I
Yeah.
take the matrices, I take their direct sum.
Yes.
This is, as a whole, not a system of
And
2n
modes.
plus 2n modes, but it's kind of. Is that correct? Or am I-
If you take the direct sum, it's a good question. I think if you just consider now a possible,
I think these operators.
Yeah.
Right. I mean, within the 2 groups of n and m fermions, they have the right exchange statistics. But in this direct sum, the operators from different blocks they fully convolute, so they don't anti-convolute, so they don't really form.
yeah, exactly. I guess
Like 2n plus m fermion.
yes. If by direct sum you mean that you now take the tensor products of,
Look at the matrices.
yeah, then no, then you construct something that is not fermionic in any way.
Good.
Yeah. Okay, so if things are clear, I mean, I introduced this big algebra of fermionic operators, which I now deleted. No, maybe it's still here. This big algebra, which is very big, exponentially large, and so on. But there is a very interesting subset of this, which I cannot not mention, which are the free fermion operators. So I have to say something about the free fermion. This time it's a B. And this I define it by considering the set Q, which is made up of operators which are quadratic in these gammas. So each operator will have certain matrix defined by certain matrix Q, A, B, gamma A, gamma B. I mean, I use this Einstein notation. I sum over the repeated indices. So this is kind of the most generic operator, which is kind of contains products of only 2. Like before, I was considering all possible products. Now I focus only the product of 2 gammas at a time. And now I also want it to be Hermitian, which turns out to be equivalent to this matrix should be Hermitian as a matrix. And you see, this is obviously a subset of this big algebra. But it's also a subalgebra. Well, it's not really a subalgebra. It's like it's a Lie algebra now, in the sense that if I have 2 such operators, the commutator will again be a quadratic operator. So it's closed under this commutator bracket, which makes it a Lie algebra. And this
is like an example of that it's not an algebra because it's not closed.
Exactly. It is an example that this does not imply that actually just products of this, well, products of this will be up to order 4, so they're not contained. Exactly. So this is related, and this is what people will call maybe quadratic Hamiltonian. or free Fermion Hamiltonians. All these words are the same. I guess maybe if you stretch it a bit, you can call them Gaussian Hamiltonians. Right. And one other property that they have is that not only that commutator is again quadratic, but also their action on linear terms in gamma is closed in the following sense that if I take the factor of I because it helps, but if I take I times a certain q and I compute the commutator with gamma A, this is again a linear operator in the gamma. So it will again be something like a certain matrix K A B gamma B. So this is again a linear operator in the gammas. And it turns out that this K, matrix K, is a matrix of the special orthogonal 2n dimensional algebra. And this is the algebra of matrices K. It's just general matrices of n dimension and real that are skew symmetric. So the transpose is minus itself. So you see that for every q, through this relation, there exists a k in that algebra. And it's actually true also the inverse. So in a sense, this space q is in a way isomorphic to the algebra SO2n. And it turns out that this is actually a proper algebra isomorphism in the sense that if I now have that q3, if I have two matrices, Q1 and Q2, two operators, Q1 and Q2, which are correspond to a certain matrix K1 and K2, then and their commutator Q3 will also have its own matrix K3, and it turns out that K3 is literally the commutator of K1 and K2 as matrices. Okay, so this mapping actually preserves the algebra structure. So this is really an isomorphism of this algebra. So this Q is a representation now of the SO2n Lie algebra. Question?
In the definition of capital Q, the
Yes.
Small q, a, b are
Yes.
complex numbers.
Yes.
Now you put the I
Yeah.
there in the commutator, and you say K are matrices with real entries.
Yes.
Is it easy to see why it is a factor I get by
yes.
converting this?
So yeah, the point is that in general Q I can take it to be complex. Doesn't matter too much, but I want it to be Hermitian. So this will have the real part of this will be symmetric, and the imaginary part will be antisymmetric. Now, if you consider the real part, the one that is symmetric, this is symmetric times these two things are actually anti-commute, so it doesn't matter. So actually, in principle, I should take Q to be imaginary. But essentially, the real part of Q just gives rise to a term that is proportional to the identity, and when I put the identity in here, it doesn't influence this anymore.
Then the I is there to make
to make it then to make this real. Yes. Yes.
Is there like a physical interpretation of the gammas? I know how to think of the N and A better, but you have to go.
The gammas are like the real part and imaginary part of A, right? Sorry?
You don't create particles or do any.
No, this is what people call the Majorana operators.
Yeah, I heard the name,
okay.
but never know how to think.
No, I think it's not as nice.
physical intuition we have for the A's and A's besides giving back words for when they create.
I mean, yeah, yeah, you're probably right that I'm just used to it.
I mean, I want to get there, but let's see how. Okay, so now I introduce these Hamiltonians. First, if you have a Hamiltonian, you also want to do the time evolution under this Hamiltonian. So I also have to introduce this set of unitaries, which I call Gaussian unitaries, which is the set of all unitaries u, which can be written as e to the I q, or q. And this is a subset of unitaries in the full Hilbert space. So it's a subset of these to the n-dimensional unitaries. It's also a subgroup because of that property. Like if you multiply these together, they are again in there. But what's interesting is that we had this relation that this action in terms of the commutator preserves the linearity of the gammas. And if you now act with these unitaries as unitaries, so with this conjugate action on the gammas, this is again preserves the linearity. So you have another matrix. And this is again a linear object with respect to this matrix. And this matrix, I mean, you can do an easy calculation. If u is e to the iq, then using that property with the commutator, it follows by a bit of Baker-Campbell-Hausdorff magic that this m is e to the k. Where and this is an object now in the special orthogonal group, which is should be precise. These are all matrices of real matrices with determinant 1, such that m times m transpose sorry for the people online, they cannot see it. The transpose is the inverse. Now, so this is also nice, and you might be. So you can also label these matrices U, sorry, these operators U by a matrix M, which is now a matrix of the special orthogonal group. And you might be tempted to say, great, now this U is a representation of the special orthogonal group, which is would mean that if you take now a U labeled by M1 and you multiply it by U labeled by M2, this should be equal to the U that is labeled by M1 times M2. So you will have that this product of unitaries inside U respects the product of the matrices in SO2N. And this is actually true, but it's true only up to a phase. Like there could be a phase appearing here. Which implies, for those who know the representation theory well, is that U Gaussian is a projective representation. This means that, I don't want to get in there, but it means it's a representation up to phases that appear. In many applications, these phases are completely like global phases that don't matter, so you can essentially consider these Gaussian unitaries as a representation of SO to the n, but sometimes you actually have to worry about these phases. Right.
Tommaso?
Yes.
The question by Ansgar again.
Yeah.
So how many fold cover of SO2 to the n, the group, is U Gaussian? Twofold.
Yeah.
Okay.
Double cover.
Double cover. Okay.
There will be a paper probably next week on the archive.
So this recording should only go online after that.
I've not said anything
structure of this universe,
Yes.
if I take 2 elements, wouldn't I get the four polygens?
Sorry, can you repeat?
So you also define each of the I and Q.
Yes.
Q has only
Quadratic. Yes.
but then if I take 2 of them, do a group operation which is multiplication, then I should get for the 4 terms.
No, I mean this is. It follows from applying this Baker-Campbell-Hausdorff expressions. Like if you consider e to the I1, e to the I2, you can always write this as e to the IQ3. Or this Q3 will be this Q3 can be written as a nested commutator of Q1 and Q2, but the commutators are all closed. Like Q is closed under commutation, so this Q3 will also be quadratic. Okay. So this was all that I wanted to say about, let's say, the algebra of fermions. And as you can see, you might say this is all some very nice abstract stuff, but what are these A's? Where do they appear? Like, I guess somebody asked, like, why should I call them creation operators, and so on? Like, in what actual systems do they appear? And there are many answers to this, but I guess I don't have time to talk about too many of them. But the one that I wanted to talk about is the ones of fermions as indistinguishable particles.
Sorry, one question.
Yes.
Why is this algebra called Clifford algebra and not just Fermion algebra? Do you know, or?
I mean, there exists a whole more general theory of Clifford algebras. This is an object that is defined more abstractly. Like, basically, this is only an example of a Clifford algebra. There is actually, I should have written Clifford 2n0 R, because this is the real Clifford algebra, which is the term where these two parameters 2n and that is equal q and t. And anyway, there is a whole, you can also have the complex one. So there's a whole larger family of these objects that are Clifford algebras, and this one where I have even dimension. Well, in principle, you could have Clifford algebras where this gamma squared to -1.
Mm-hmm.
This would be if you have something here that is not 0. Like you can do more generic stuff, essentially.
And why the reals? You said the span complex?
Yeah, I mean, in this case of operators, it makes sense to take the complex span. But if you want to talk about it as an algebra, you probably, to be more precise, you talk about the real span in that case. And somehow, if you have the complex span, and now I don't remember exactly what is the definition of the complex Clifford. I think I don't remember exactly, but I just know that they also exist, and they're in principle a more generic, more general object now. But I don't know what are other concrete applications. You should ask a mathematician, but probably they exist. So now I wanted to talk about how fermions appear, like how the cloud structure appear if you start considering indistinguishable particles. And this, maybe it's something that people who do quantum information, it's not something they think about every day, so it could be interesting to some. But I also think this is where fermions originally come from, and why they're called fermions, so it's important. So now I want to talk about indistinguishable particles. So first I need to talk about particles, and I'm going to talk about particles in a box. You know, the quantum mechanics one particle in a box. So I will consider what is the Hilbert space of one particle in a box. So H1 and a 1D box, so interval. This is the space of L2 functions on this interval. Right? This is kind of what the textbook of quantum mechanics will tell you. And in principle, you can also consider a higher dimensional box, so not be sublime, but like square or cube, whatever, but it all is more or less the same. So for simplicity, I will consider this 1D case. And this means the space of functions, wave functions psi, from this interval to the complex numbers, such that their integral, their square integral. So, and this is a Hilbert space, and one can also define orthogonal bases of this, of functions phi k. Which, I mean, there are many possible bases, but maybe your favorite one should be the plane wave. So this is just a set of functions labeled by index k in the integers, and this turns out to be a basis of this space. But for all that follows, you could take phi k to really be your favorite base. It doesn't have to be plane waves. So this is the space of one particle, but now we want to have many particles, and in particular, we got two particles. This would be the tensor product of twice the single particle Hilbert space, which actually turns out to be equivalent to the L2 space of twice this interval. So this is a space of functions, which now take inputs in the line, which represent the position of the first particle and position of the second particle, and give you a complex amplitude. Again, such that when you integrate with respect to both particles, right, now psi is a function of the position of the two particles. If you take the absolute value square, you integrate over the whole available space, this is fine. And of course, you can continue this construction to more and more particles, and you will eventually get the Hilbert space Hn, which is the space of small n particles, and this will be represented by wave functions psi of, you know, with n small n entries, which represent all the particles. And now I want to define the total Hilbert space of all these possible many particles, and this I take by definition to be just the sum of all possible finite particle number, fixed particle number Hilbert spaces. So all this Hn, I combine all of them for n going from 0 to infinity. The H0 is just the Hilbert space with one state, which is the state in which there are no particles. So if I kind of consider the union of all these possible Hilbert spaces, I construct a very big Hilbert space which contains all possible many particle states. Right. Now these were particles and they were distinguishable in the sense that if I consider, for example, a two-particle wave function, this will have two. For them. If I consider the wave function psi of two positions x and y, this means what is the amplitude that the first particle is in the position x and the second particle is in the position y, right? And if I now consider psi yx, this means what is the probability amplitude that the first particle is in position y and the second one in position x. And these two are two unrelated, let's say, two independent states, right? Because the two particles are two separate particles. I can say where is the particle 1 and where is the particle 2 and what's the probability that 2 is here and 1 is here. There's no reason why this should be here. But now I want to impose some kind of symmetry on my states that implies that the particles are indistinguishable. So in particular, it doesn't really make sense anymore to say where is the first particle and where is the second particle, because first and second particle should be indistinguishable. I can no longer say which one is the first and which one is the second. So the only question that it should make sense to ask is what is the probability that there is a particle here and a particle there. Doesn't matter which one is the first and which one is the second. So in particular, it's two quantities, both refer to the state there is a particle in x and there is a particle in y. So in this symmetric case in which they are indistinguishable, these two should be somehow related or equal. Another way to see it is that if you have a state, a wave function of a certain number of particles, and these particles are indistinguishable, the state should be, now you can close your eyes and I switch two of the particles, the state should be completely invariant. So when you open your eyes again, you should not notice that anything has happened. So this, if the particles are indistinguishable, then the states should all be completely invariant under switching any two particles. In particular, so here I wrote equal, but you know that in quantum mechanics, states that differ by a global phase are essentially the same state. So one could also consider the possibility of having here a phase alpha. Alpha is a complex number of modulus 1. And this, all the statements I made before, these two would represent the same state, and the particles would be equally indistinguishable. More generally, if I have a many particle state, I want to consider only those states where if I now take any two of these x's and exchange them, then the state is invariant up to this global, or the wave function is invariant up to this global phase. So yeah, here I switched and the xj and xk, and this should give me the same wave function up to a phase. Now, of course, switching two particles, if you do it twice, you go back to the same. So now this function psi has this symmetry, and now I do it again. Here I will get alpha, another alpha will come out, and I will get alpha squared psi. So I have that alpha squared should be 1. This should be equal to that. This psi here is exactly the same psi here, and so alpha squared should be 1. So actually, if I want this to be true, there are only two possible choices of alpha, which are +1 and -1. If I choose +1, so the functions are symmetric under exchange of particles, then I get. If I choose -1, that's the case that we are interested in, because in this case I get fermions. So saying that I'm considering indistinguishable fermions means that I am considering wave functions of this type such that they are antisymmetric under exchange of any two arguments of the function. Yes.
But you are assuming that any way to exchange the two particles is the same.
Yes, of course. There is another option, which is that when I exchange the first with the second, I get a plus. When I exchange the second with the third, I get a minus, and so on, some other weird mixture.
I'm referring to like depending on if you think about not because there would not be a physical process that instantaneously changes. So you have to think about the physical process of the world lines of particles, and then the fact that it doesn't matter how you permute them is a property of whatever space-time dimensions.
I guess you can phrase these things also in that way, but here I'm talking about it at a more fundamental level. Like I don't want to actually start exchanging these particles. I'm just saying I consider a wave function that has this property that it's the same if I exchange two entries, and this for me means that exactly. If there was a godlike creature that could do this exchange instantly, and I close my eyes, somebody does it, and I open them again, I will not see any difference. Any observation I can make will not reveal any.
Like there is physical theories in the three space-time dimensions in which you can have a difference by making some.
Well, this is not what I'm considering. Yes. Right.
But this would.
Sure.
I'm just trying to figure out what are the assumptions and what is coming out of it. So and you are explicitly assuming it. I cannot tell.
Yeah. I am assuming in the end what I want to do is to assume that the wave functions are antisymmetric. So if somebody switches them, if one gives me exactly the same state except that they're switched, I will not be able to tell this apart. So this is my assumption. Now I was trying to give a motivation why I would want to make this assumption, and maybe you can argue that you could make other assumptions based on other motivations, but I think this should be relatively clear, right? But maybe you can argue my motivations are, or you could do something more general, and maybe yes, I guess.
I think the argument was clear. I just wanted to find the exact borders.
Sure. And I know that there exist these animals and stuff. I have to say that if somebody gave a lecture exactly where they come out of in this sense, I would be very interested. So, right, but now I don't care. I just want my functions to be invariant if I could switch the particles without causing any other perturbation to the system. And I would like to consider essentially the subspace of wave functions that have this property, and this is what I will call H n minus. This just the space of wave functions of n particles, such that by now that we permute these, so have some kind of permutation of these indices. Any permutation. This will give me the same wave function up to a sign. And the sign depends on how many two particle swaps there are included in this permutation. So this is the sign of the permutation. For any permutation in the permutation group. Do I have still time? And I will consider this the fermionic Hilbert space or Fock space. I guess this is what people call it as the sum of all such n-particle antisymmetric spaces. Okay, so now we can come to the punchline, which is that if I have such a space, there exists in there this operators gamma that we considered before. And I will show you just by constructing. And I mean, before we constructed the gamma, well, we defined the gammas and we constructed the alphas out, sorry, the A's out of them. Now I will do the other way around. So I will construct these A's, and then from them one can derive the gammas. Because, I mean, they're equivalent. So I will define an operator, A dagger, okay, which takes an operator on this space H minus that I defined. In particular, it takes input a wave function psi, which presumably belongs to the n particle subspace. And this will give you as output a dagger psi. Is a new wave function that now is in the n+1 particle subspace. So this a dagger takes a state in the n particle sector and creates a state in the n+1 particle sector. So it adds a particle. And I mean, if we define it for all wave functions in the n particle subspaces for all n, then by linearity, this is defined on the whole of the fermionic Fock space. And now I can tell you how this is defined. So this AK dagger psi. This is an n+1 particle wave function, so it will take n+1 entries. And this is equal to psi is equal to psi, which has with the first n coordinates. And then I multiply this by the n+1 coordinate in the state phi k, which is, I don't know if it's still there, was the basis, one of the basis states, the kth basis state of the one particle subsector. So these phi k's are one particle wave function, so they take one input, and I put here n+1. And now if you're paying attention, you will say, oh, but this is not antisymmetric. So it doesn't really belong to the space, and that's true. That's why I also need to antisymmetrize. So I'm going to sum this over all possible permutations of these coordinates. With the sign of the permutation, this makes it kind of by construction an antisymmetric wave function, so everything is correct. And then I have to put a normalization factor, which just make things make more sense later.
What's it? So what's the vector? Now it's even hard to read for me.
I guess the point is that it's not so important, but it's a fraction where the numerator is square root of n+1.
Yeah.
And the denominator is the factorial of n+1. Okay. And now I can also define the operator A, which is also an operator on this space, which now takes as input a function, again, it takes as input a function of n particle. It will give me a function of n-1 particles. And the definition is even easier because I now want to tell you what is the wave function AK psi. I need to define a function of n-1 entries. and this will be equal to, again, a factor of square root of n. And now I take this wave function, which has too many entries. Now it should have n minus 1, now it has n. And so I basically project out the last coordinate by integrating it onto, again, 5k stuff. So basically taking this n particle state and projecting out one particle in this phi k state. While here I'm taking the n particle state and adding one particle in the phi k state.
But sorry, should the variable be xn, not xn plus 1?
Yes.
Yeah.
So yeah, this is the variable I am supposed to. This is the variable I'm integrating out. That's true.
So I have an AK for every basis state in my.
Correct. Yes. Now I've written them in this way. Makes it look like they are a Hermitian conjugate of each other, and indeed they are. So if I have 10 minutes, yes.
Why is the star there at APX side?
It's complex conjugate. Because like if you want to, let's say the bra of this phi k in this silver space is integrating with respect to the conjugate. So in particular, like, yeah, exactly. If you consider this inner product of this Hilbert space of two functions, where now psi and theta are wave functions, then what is this? This is the integral if we assume that psi has n particles, then ak psi has n minus 1. Therefore, also theta has to have n minus 1, otherwise everything is 0. And in this case, this is the expression of the inner product by definition. And if we now write out what we wrote before for A, this will be equal to, again, integral rho squared to n. This is just a definition of a k that I wrote there. Right, and now if you look at this thing and you rearrange things around, you take out all the integrals to the front and commute a bit some of these things, you can really rewrite this as the following. So this is as Raul notes. So basically I put all the things with a star inside here. And now you see that this is just the integral of this object with this one. And this object is antisymmetric with respect to exchanging all the coordinates. So if this is antisymmetric and I'm integrating something with it, then for free I can put here an antisymmetrization of this one. So I can put here for free this sum over permutations. Maybe I should do it properly. But the point is that if you put in this antisymmetrization, and you also put in this n factorial, because they're all with the same weight, then the object inside the square brackets, if you look at it here, you recognize that this is just a dagger k acting on theta. So this is just a So if you compare these two, this by definition shows that a dagger is the dagger of A.
So
Yeah, sorry.
I still don't completely understand like, where you get the phi k from. It's just a basis or?
Yeah, phi k is, I define it here. So there is a single particle Hilbert space, which is just spaces on of functions on the line or on the interval. And as I said, you just pick. I put there the plane wave basis because it's nice, but you can also put, you know, whatever Hermite polynomials that you have.
And also, sorry, so your proof assumes that theta is like n or n minus 1 or whatever a wave function, a particle wave function and size the one again. Or
Size n
size n
and theta is n minus 1. Yeah.
But and then by usual linearity and continuity, this extends to the
Exactly.
I found interesting question.
Yes.
Is that this looks at an often like a Fourier transform, right? So that principle they can make this sort of Fourier transform. Okay.
Not really, but A.
If I would insert the bandwidth basis,
Yes.
then
I mean, and then this is like would be like some in a way the Fourier transform of this psi with respect to the last coordinate, something like this. Yes. Yeah, but I think you should really understand it as projecting out a particle in that Fourier state, and that one is adding a particle in that state. Okay. Yeah, I don't have much more time, but the point is that by doing similar tricks, you can also convince yourself, for example, that which of course is equal to that they anti-commute. I guess I don't have time to write it out, but you really write this out, and then this, for example, this one, acting twice with AJ and AK will create an integral with respect to these phi k and phi j with respect to the last two variables. But then you can always like switch these two variables up to a sign, and that's the same as integrating out first k and then j rather than first j and then. So if you're interested, ask me, but this is true. And also maybe a little bit more complicated, but with the same function analysis tricks, you can also show this. That the anti-commutator of A with A dagger is 0 unless J and K are the same, in which case it's proportional to the identity. And of course, this implies that now if you construct the gammas out of these, the way that I also wrote before, these will satisfy this Clifford algebra as I wrote at the start. So now, in this sense, the A's and the A daggers, I think you can legitimately call them creation annihilation operators. What do the gammas here do? I don't know if they create a superposition of having added one in a row. Right. So, I mean, there would have been more things that I wanted to tell you, but I don't think I have more time. So, I guess I should stop.
A question.
Question.
So when can I see with this like wave function representation so quickly that when I want to add a particle where there already is one, that it's zero?
I mean, it follows from this, right?
Yeah.
If you want
not
to.
in this.
Well, okay, so maybe. So I think this is the best way to prove it in general. But if you want, maybe one can look at the most trivial example, right? You have a particle already in the 5K state. So this is your wave function. Like your initial wave function does have one particle in that state. And now you want to add a particle in the same K state. This will be a wave function of two particles, which in particular will be equal to the constants, the anti-symmetrized product of these two. So but this object is symmetric with these two variables, right? But it's the same. So when you anti-symmetrize, you get zero. And this, of course, generalizes to however many particles. Yeah. So yeah, maybe. Yeah, go ahead. But maybe I just want to say the last thing, just to conclude this topic, is that so if these objects exist, like these A's and gammas and so on, then this whole theorem that I stated at the beginning also is true, which means that there should exist this basis of states. And it turns out that these states are, well, they exist and they have this form. So it's just a product of these fundamental basis elements, and these K's are basically all the indices where n is 1. So if n is 0, I don't have anything in here. If n is 1, I have a phi corresponding to that index. Sorry? Sign. And yeah, of course, anti-symmetric, because everything has to be anti-symmetric, but up to the anti-symmetrization, this is really just a product state with all the particles in the occupied states. And this is what people call this later determinant states. Because this is, if you look at the expression of this is literally the determinant of a matrix. M. You call M ij phi ki j. If you define this in this way and write the expression of the determinant, you get this. That's why it's called later determinant. Yes. Sorry.
All of the states depend on the positions of the particle, or like what are the
Yeah. This would be the wave function of this space. So I guess maybe you could write it this way. Yes, that makes sense.
So where in the font space, where did the N, capital N now come from?
Yes. So basically, you have I've defined 1A and 1A dagger for each element of the basis of the one particle space. So this leads to 2 gammas for each basis element of the particle space. So in particular, if we want to have 2 n gammas, which is what we started with, we need n basis functions of the one particle space. So capital N is basically is the dimension of this space.
Is this when people in quantum chemistry say that they hit their basis functions?
Yes. So, I mean, here I cheated because now this H1 is infinite dimensional, right?
Exactly.
But, so I actually reconstructed here something that is a bit more general than what I started with. I constructed something where capital N is infinite. But, of course, you can also consider, you can redo this whole construction with whatever H1 you prefer. I could, for example, discretize this thing and have that my particles can only occupy a finite discrete points in space. Then I would get like a lattice system and would have a finite basis, which is just the number of sites that the particle can occupy. So n in that case would be the number of sites that my particle can be in. And the point is that this kind of should connect at the beginning. I was saying this is what is this number of modes? Basically, the number of modes is the number of independent one particle states that you can have in this interpretation. So yeah, and then the full Hilbert space is where you occupy each of these one particle states with either 0 or 1 particle. Yes.
And this determinant sort of picture, is this also the reason why these learning fermionic system results are kind of easy as efficient because of this easiness of computing a determinant in reverse, basically?
Yeah, I mean, it's kind of also related to this whole free fermion picture that I described at some point. So these later determinant states are free fermion states in the sense that you can write this as a Gaussian unitary acting on the vacuum state, on the 0 fermion state. It's not so maybe easy to see in this picture, but you can always write it in this way. So these states are Gaussian states. Actually, not all Gaussian states can be written in this way, but these are Gaussian. These can be written as Gaussian states. And right, so ultimately, when you look at Gaussian states, we said this is giving you essentially a representation of SO to N. So you can describe all these objects in terms of some matrices N, which are 2n dimensional. So you can describe states and operators in an exponentially large dimensional Hilbert space in terms of polynomially dimensional matrices. And it turns out that all the interesting things that you want to compute will be somehow related to the determinants of this M. Like this M here is probably not the same as this M, but still ultimately everything that you want will be written in terms of determinants of products of 2n dimensional matrices, which is in the end efficient.
Yeah, but I mean, depending of course on the learning path, but there's no reason to restrict yourself to pre-fermionic state, right? Because the determinant picture is true for any fermionic state.
No, I mean, it depends what you mean by determinant picture. Like this is a basis of all fermionic states, yes. But if I now have to learn a state which is an arbitrary superposition of all possible states of this form, then this, it's not a simple determinant picture, I would say. This becomes hard. The reason why you want to restrict yourself to free fermion or Gaussian states is because they're easy.
Okay, there's no further question. Let's end the time.